Good evening, sir.
Good evening, ma'am.
You can start now, sir.
Okay, okay, thank you. Good evening, students. So we have been discussing the concept of AC circuit for the past few days, and today I will be discussing the concept of wireless current, choke coil, and the LC oscillation. Okay. So all these topics we are going to discuss today. So I will be sharing my whiteboard with you. So first of all, I will be discussing with you the concept of wireless current.
Sir, your voice is breaking, sir.
Can you hear me, ma'am?
Yeah, I can hear you, but voice is breaking.
Okay, maybe a little bit signal issues here, ma'am. So I think it will be automatically corrected.
Okay, sir. Thank you, sir.
Okay. Okay. So what is meant by wireless current? Actually, the component. Okay, the component of current which does not contribute. Does not contribute to the average power dissipation. This is called wireless current. Okay. This is called wireless current. So what is the meaning of that? So if we want to know that, we need to understand this graph. Okay. So let me draw that graph here. So the IRM, okay, the total current IRM is along the x-axis, and the EMF, RMS value of EMF, it is oriented like this. Okay, so this is ERM, and you have a phase difference of phi. So here, if you resolve this component of IRM along the direction of this ERMS, it will be IRMS cos phi here. So here it is IRMS cos phi, because you have the angle phi here, and if you resolve this, it will be IRMS cos phi here, and the another component which is oriented on the other side, that is IRMS sin phi. Okay, so here you see this component. This component is IRMS sin phi. So now what is the wattless current? The wattless current is this component, IRMS sin phi. Okay, so it is the component of current perpendicular to this EMF, that is ERM. Okay, so here amplitude of the wattless current is given by amplitude of wattless current. It is nothing but IRMS sin phi. So this component IRMS sin phi is actually perpendicular to ERMS, and how can you find out the instantaneous value of this wattless current? So the instantaneous value of this wattless current is equal to, how can you find out this instantaneous value? That is I naught sin phi. I naught, you know very well, the amplitude. Okay, so I naught sin phi into cos omega t. So this is the equation for finding the instantaneous value of wattless current. That is I naught sin phi into cos omega t. So what is the phase difference of this wattless current and the voltage? Okay, so as I have mentioned earlier, this IRMS sin phi maintains a phase difference of pi by 2 always with the ERMS. So it does not contribute to the average power dissipation. Okay, and now the next thing is, the next point regarding to this wattless current is the RMS value of wattless current. So RMS value of wattless current. The RMS value of wattless current is nothing but I naught by root 2 sin phi. That is I naught by root 2 sin phi. Okay. So these are the points regarding to the wattless current, and the only thing is you need to remember all the formula and equation. So there is nothing much about it. So now we are moving on to our next concept, that is choke coil. Okay, choke coil. Students, have you ever heard of this term choke coil anywhere? Have you ever heard of this term choke coil? Yes, students, anyone? Just tell me whatever comes to your mind when you hear this term choke coil. Have you ever come across this term?
No, sir.
Okay. In your automobile, you can find this choke coil. Okay. Of course, in latest model of automobile, you may not be having this choke coil, but earlier when automobiles were being manufactured and marketed, okay. So in those times, you will be having a choke coil in your automobile, in your two-wheeler. Okay, especially if you want to understand this easily, I have to give you the example of two-wheeler. In your two-wheeler, you will be you will have this choke coil. So there, actually, what happens is this choke coil can release an enormous amount of energy in a short period of time. That was the purpose of choke coil used in that earlier model of automobile. Okay, so the choke coil was used whenever your automobile has a starting problem. Whenever you find difficulty in starting the engine of the two-wheeler, what is the last thing they used to do is that they just press the choke coil, and due to the pressing of choke coil, a large amount of energy is released in a short amount of time. So here choke coil is actually used to supply large amount of electrical energy in circuit. So what is the purpose of choke coil? Here actually in AC circuit, okay, the current can be reduced by using a choke coil. Okay, so this choke coil is nothing but a copper coil. Okay, this choke coil is actually used in AC circuit. Okay, it is used in AC circuit to reduce the current. Okay, to reduce the current with minimal loss of energy. With minimal loss of energy. Okay, so this choke coil is nothing but a copper coil. Okay, so this choke coil is nothing but a copper coil. It is a copper coil wound over a soft iron laminated core. Okay, and this coil is always used in series in the AC circuit, in which the current is to be reduced, and it is otherwise called as ballast. Okay, the choke coil is otherwise called as ballast. So choke coil is otherwise called ballast. Okay. So usually a circuit with a choke coil, it is nothing but a series LR circuit. Okay. So the resistance of the choke coil is very small, and since it is used in a LR circuit. Okay. LR circuit means a circuit with a inductor and resistor. So in the LR circuit, what is the value of current? That is E by Z. Z is nothing but the impedance. Here, your Z is given by square root of capital R plus small r, the whole square, plus omega n. Okay, plus omega n, the whole square. So here, the small r is nothing but resistance of the choke coil. Okay, it is the resistance of choke coil. And the power loss in the choke coil, as I have told you, this circuit or the choke coil works with minimal loss of energy. Okay, minimal loss of energy means the average value of power loss. If I represent it by this symbol, okay, average value of the power loss is equal to VRMS into IRMS cos phi. And this tends to 0 actually. That means the power loss is actually very, very minimal, and that tends to 0 here. And now what is the value of your cos? So cos phi is nothing but your internal resistance divided by the total impedance. So that will be small r divided by root of r square plus here omega square L square. So this is the value of your cos phi. And in choke coil, you won't be having that much of equation. So just these equations are enough to solve numerical problems involving choke coil. Okay. So not much of concepts are involved here. So you just remember these formula and equations, and you will be able to solve the numerical problem. And now we will be moving on to the concept of LC oscillation. Okay, LC oscillation. And before going into detailed concepts of these LC oscillation, let me ask you a basic question. What is the meaning of oscillation in general? What is the meaning of oscillation in general? Yes, students. Can anyone tell me what is the meaning of oscillation in general?
So,
Yes.
so to and fro movement, sir, from one position, from the mean position and back, sir.
Yes, you are right. It is actually the to and fro motion. You can take a very simple example, that is a simple pendulum. Okay, that's a common example. A simple pendulum, you can see the to and fro movement. Okay, of the bob of the pendulum. To and fro means it moves from here to there. Okay. So, what is the analogy of the term as oscillation with the LC circuit? So, LC means you will be having an inductor coil. Okay, inductor coil and a capacitor in series. Okay, inductor coil and capacitor in series in an AC circuit, that is called LC circuit actually. Okay, so what is the form of energy stored in an inductor coil? What form of energy? Can anyone tell me? what form of energy is stored in an inductor coil? Yes, students, what form of energy is stored in inductor coil? Yes, students, what form of energy is stored in inductor coil? What form of energy is stored in inductor coil? That is magnetic field. Okay, energy is stored in the form of magnetic field here. Okay, and what form of energy is stored in capacitor?
So potential, sir, electrostatic potential.
Electric energy actually. Okay, electric field or electrical energy. So here energy is stored in the form of electric field. Okay. So when you have an LC circuit and you supply some energy to the LC circuit, what happens is, according to the law of conservation of energy, the total energy actually oscillates back and forth between the electric field of the capacitor and magnetic field of the inductor. Okay. So you can understand this very well when you consider the concept of mechanical energy. You know very well the forms of mechanical energy are potential energy and kinetic energy. Okay. So when an object is having potential energy in total, so for that let me draw a diagram here. So this is the ground level. Okay. And you consider an object here. You consider an object here, a spherical object or any object. Okay, that doesn't matter. And it is at particular height. It is at particular height h from the ground level. So this object is at a height h from the ground level. Okay. Now it has been taken to the height h from the ground level, and now it is in a state of rest. Okay. So you all know very well the concept of potential energy and kinetic energy. So the body is having the mass m. Okay. Now what will be the value of potential energy here for this body at this height h? What is the value of potential energy? Students, what is the value of potential energy for this object at this height h? It's a general question actually.
Sir,
Okay.
MGH, sir.
MGH. You are absolutely right, MGH. What is the value of kinetic energy here? What is
Sir,
the
half
value of
MV
kinetic?
square. Half MV square.
Now it is at rest. Okay, it is at rest. What is the
Sir,
value
zero,
of?
sir. Zero.
It is 0. Okay. So since the total energy is equal to, so the total energy is the sum of potential and kinetic energy. Okay. The total energy is a sum of potential energy and kinetic energy. Okay. So in this scenario, when the object is at certain height h and it is at rest, the total energy is stored in the form of potential energy and its value is mgh. So the kinetic energy is 0. Okay. The total energy is mgh. As the body starts to fall towards the earth, Okay. What will happen to the potential energy and what will happen to the kinetic energy? I am asking you in a qualitative manner. Okay. As the body starts falling towards the ground, what will happen to the value of potential energy and what will happen to the value of kinetic energy? I need a qualitative answer only. I don't need the exact values and all. Okay. I'm just asking you.
So,
Yes.
sir, it will be conserved, sir. It won't change.
What will happen? Can you repeat that?
Sir, it will be conserved, sir.
Yes, of course, the total energy is conserved. But what I'm asking is, what will happen to the value of potential energy and kinetic energy? The
Sir,
total
it will
energy,
interchange, sir. Potential will become zero, kinetic will become equal to potential, sir.
can you be more specific and more clear? I'm just
Sir,
asking.
yes, sir. Potential will become zero, sir, and kinetic will become mgh, sir.
At which point?
Sir, at the ground point, sir, when it reaches the
At
ground.
the ground level. At the ground level,
Yes, sir.
Your total energy will be stored in the form of kinetic energy, and your potential energy will be zero at the ground level. Okay, that is the total energy is conserved. And during the course of its journey from the height h to the ground level, the potential energy value decreases and the kinetic energy value increases. Okay, so that the total energy is constant. Okay, the sum of the potential and kinetic energy at each point during its journey, it remains constant. But the value of potential energy decreases when it moves towards the ground, and the value of kinetic energy increases, but the total energy remains constant. And when it reaches the ground level, the entire energy is converted into kinetic energy so that the potential energy becomes zero. So this is the concept of mechanical energy conservation. Okay. So energy can neither be created nor be destroyed, that you know very well. Here we have discussed the concept of mechanical energy. Similarly, okay, when you can understand this concept very well, this concept of mechanical energy conservation very well, you can easily understand the concept of LC oscillations as well. So when you have an LC circuit, that is an inductor coil and capacitor in a circuit in series. Okay, when you supply some energy to this circuit, initially the total energy stored in the form of electric field, the magnetic field will be zero. Okay, and in course of time, what happens is the energy stored in the form of electric field actually decreases, and the energy stored in the form of magnetic field increases in course of time. And after a certain period of time, the total energy will be stored in the form of magnetic field, and the total energy will be entirely of the magnetic field, but the energy stored in the form of electric field is zero. Okay. So here the total energy has been shifted from electric field to magnetic field. Okay, in course of time, step by step. After a certain period of time, the cycle repeats. Okay, the total energy actually the energy stored in the form of magnetic field decreases and the energy stored in the form of electric field increases. So this is called LC oscillation. Okay, the total energy actually oscillates between the electric and magnetic field. This is the concept of LC oscillation. Okay, and now when we want to understand this LC oscillation, we have to understand a circuit. Okay, so for that I will be erasing all these things. Since this is not required for our discussion, I have just given you an example for the total energy conservation. Okay, so I will be drawing this circuit. So this is your inductor coil. Okay, L represented by the letter L. And here you are having the capacity. Okay, this is the capacity. So here, so let me explain you step by step. The first situation, okay, the first situation. Here you are having a capacitor, okay, with charge Q0. It is connected to inductor of inductance L. Initially, the capacitor is charged. Okay, initially the capacitor is charged, and you are having an inductor coil of inductance L. So this is the value of your capacitor, and initially at time t equal to 0. At time t equal to 0 means your capacitor is having the total charge Q0. So the energy stored in the capacitor is maximum. That means your electric energy, that is electric field energy, that is represented by U at E0. That is your maximum value of energy. So that is Q0 squared by 2C. This is the energy stored in the capacitor equation. Q squared by 2C is the expression. Here you are having the charge Q0. So the energy stored in the capacitor is now Q0 squared by 2C. So the total energy in the circuit is this much, Q0 squared by 2C, and this is totally in the form of electric field. At the same time, the current in the inductor is 0. Okay, the current in the inductor is 0. There is no current flowing. Current in inductor is equal to 0. So energy stored in it is also 0. U suffix B is equal to 0. So total energy is fully electrical now. So what is the value of total energy? So now what is happening? I am not able to use the whiteboard. Okay. So here the total energy E is given by U E0 plus UB. So Q0 squared by 2C. It is the total energy for this scenario. Okay. It is fully electric. And after some time, okay, after some time, since the charged capacitor is connected to this inductor coil, what happens is the capacitor starts to discharge. Okay, the capacitor starts to discharge after some time. The capacitor starts discharging. Discharging means charges will flow through the AC circuit. When charges flow through the AC circuit, okay, charges will flow across the inductor coil as well. So when the charges flow across the inductor coil, a current is established in the circuit. Okay, so current is established in the circuit. in the circuit and current flows through the inductor. Okay, current flows through the inductor, and of course current flows in the direction clockwise. Okay, so clockwise current starts flowing through the inductor. Clockwise current starts flowing through the inductor. So at any particular instant of time, at this particular instant of time, let us consider current as I. Okay. So due to the discharging of capacitor, charge on the capacitor decreases. So what will happen? The electrical energy actually decreases. Okay, because the capacitor starts discharging. That means the electrical energy actually decreases. At the same time, current starts flowing through the inductor and they will be getting clockwise current. So the current, though the energy stored in the form of magnetic field in the inductor increases. So UB actually increases. So what is the value of UB? That is half Li square. And at that particular instant of time, the charge stored in the capacitor is Q. Okay. So the electrical energy is Q squared by 2. You can find differences in this value of charge. Initially, the total charge is Q naught. Okay. So the total energy stored in the capacitor is Q naught squared by 2C. And now the charges have been reduced to small letter q. So now the electrical energy stored in the capacitor, it is Q squared by 2C. This is the value of electrical energy. Okay. So the magnetic field energy is given by UB equal to half Li squared. So at this instant, your total energy will be the sum. Okay, the total energy will be the sum of electrical and magnetic field energy. So total energy equal to UE plus UB. So here it is Q squared by 2C plus half Li squared. Okay. So this is the total energy at this point of time. Okay. So now we are moving on to our next scenario. After some time, the charge in the capacitor is exhausted now. Okay. The charge in the capacitor is now exhausted. So what will happen? The total electrical energy will be 0. Okay, the third instant of time or the third scenario, the charge is stored in the capacitor is exhausted due to the continuous discharge of capacitor. The charge in capacitor becomes 0. Okay, since the capacitor is discharging, the charge becomes 0. So charge becomes 0 means the total electrical energy UE will be equal to 0. And at this point, the magnetic energy is maximum. Your UB, that is energy stored in the form of magnetic field, it is maximum. That is stored in inductor. Okay. So current is also maximum. Current is also maximum. That will be I naught. Okay. The value of maximum current is I naught. Now, what is the value of this magnetic field energy? So that will be UB naught, that is half L I naught square. Okay. So this is also equal to the total energy of the system. Okay, the total energy here, the total energy is maximum. The total energy is constant, but the total energy is stored in the form of magnetic field only, and the electrical energy is zero. Okay. So now you can realize that the total energy oscillates between electric and magnetic field. Okay. So now the total energy is stored in the form of magnetic field. So after some time, what happens? So now there is no charge on the capacitor and it is exhausted. So current cannot be maintained, okay, because capacitor actually stores charges and then they supply current. But here the charge is actually exhausted in capacitor. Okay, the charge is actually exhausted in capacitor. So what happens is the current starts decreasing. Current starts decreasing in the circuit. So since the current starts decreasing, so now what will happen? The inductor tries to oppose the decay of current. Okay, inductor tries to oppose the decay of current. This is based on Lenz's law. Okay, inductor tries to oppose the decay of current and it supplies its own energy to maintain the current in the circuit. It supplies its own energy. So inductor, it supplies its own energy. So what happens is the energy stored in the form of magnetic field actually will be converted to electrical energy by charging the capacitor. Now the capacitor starts to charge again. So what happens is a part of the energy from inductor, okay, a part of energy from inductor is converted to capacitor. A part of energy from inductor is converted to electrical energy in capacitor by charging the capacitor. Okay. So here also the total energy is the sum of electrical and magnetic energy. But here it is partially magnetic and partially electric. Okay. So it is partially magnetic field energy, that is QB, and partially electric field energy, UE. So after some time what happens is, due to the continuous charging of capacitor, at one point all the energy from the inductor, okay, all the energy from the inductor is transferred to the capacitor. So the total energy is now electrical. Okay. So this is what happens in LC circuit. Okay. So in this scenario, what happens is, after some time, inductor loses all of its energy. Inductor loses all of its energy and current becomes zero. Current becomes zero, but the capacitor is now fully charged. Okay, capacitor is fully charged. Fully charged to the original value of charge, that is Q0. So now the total energy is fully electrical UE is equal to Q naught squared by 2C, and UB will be equal to 0. So this is how NC oscillations happen in this circuit. Okay. So here the process of charging and discharging of capacitor and flowing of current through the inductor, it happens again and again. And this concept is called NC oscillation. And in this process, you will be getting NC oscillations for definite frequency. Okay. So when the current flowing through the circuit is maximum, that is the total energy stored in inductor. Okay. When current is maximum, that is I naught. Okay. Your total energy is magnetic. So in that case, U B naught equal to half L I naught square. So the total electrical energy is Q naught squared by 2C, total magnetic energy, or it can be otherwise called maximum value of electrical energy. Maximum value of electrical energy. And this is the maximum value of magnetic energy. Okay. So both these energies are actually equal, okay, because the total energy is conserved. So this is the total electrical energy, this is the total magnetic energy. Actually, energy can neither be created nor be destroyed. So half L I naught square will be equal to half Q naught square by C. So this half and half will be cancelled, and in this process you can find out the value of I naught. That will be Q naught by square root of LC. This is the maximum value of current, Q naught by root of LC. Okay. So this is the concept of LC oscillation, and you will be having some mathematical treatment of LC oscillations as well. We shall discuss that also now. Okay. Mathematical treatment of LC oscillation. We shall be discussing that now. So mathematical treatment of LC oscillation. So here from the Kirchhoff voltage law, okay, you can apply the Kirchhoff voltage law to this circuit. To this circuit, you can apply the Kirchhoff voltage law. So when you apply the Kirchhoff voltage law, the voltage across this capacitor is given by Q by C. Okay, and the EMF across this inductor coil is given by L into di by dt. Okay. So the voltage across this capacitor is Q by C, and EMF across this inductor is L into di by dt. Based on Kirchhoff voltage law, the equation is, because the voltage through the capacitor is in opposite direction to the voltage across the inductor, that is L into di by dt equal to 0. So here, actually, due to the flow of this current, okay, there is a decreasing charge in the capacitor. As you know very well, when the capacitor starts decreasing, okay, when the capacitor starts discharging, the current flowing through the capacitor increases. So the current is actually equal to minus dq by dt. So here instead of I, you can apply this minus dq by dt. So your q by c minus L d by dt of minus dq by dt. That will be equal to 0. So this will be q by c plus L into d squared q by dt square equal to 0. So you can rearrange this differential equation in another form. After rearranging, you will be getting d squared cube by dt square plus 1 by LC into Q equal to 0. Okay. So when you divide this equation by L, you will be getting like this: d squared Q by dt square plus 1 by LC into Q equal to 0. So when you compare this equation with the equation for simple harmonic oscillator, that is d squared x by dt square plus omega square x equal to 0. When you compare both these things, we will be getting omega equal to 1 by square root of LC. Because when you compare both these things, your omega square is actually equal to 1 by LC. So omega equal to 1 by root of LC. So you know very well omega equal to 2 pi into F. So here 2 pi into F equal to 1 by root of LC. So that means F equal to 1 by 2 pi root of LC. Okay, F equal to 1 by 2 pi root of LC. Root of LC. So this is the expression for frequency. And now in general, the variation of charge in the circuit is given by Q is equal to Q naught cos omega t. Why we are using cosine function here? Because initially the total charge is maximum in the capacitor. Okay, because when the capacitor is fully charged, your charge value is maximum. So a cosine function actually starts with the maximum value. So here the cosine wave actually starts from the maximum and goes on like this. Similarly here in this LC circuit, the capacitor stores the maximum amount of charge, so it is a cosine function. Q equal to Q naught cos omega t. And current in the circuit, LC circuit, is given by I equal to I naught sin within the bracket omega t minus pi by 2. Okay. I naught sin omega t minus pi by 2. Actually this is just minus pi by 2. So omega t minus pi by 2. So based on this I, you can write the value of Q. Okay, because we know very well I equal to minus dq by dt. So when you use this equation, your Q is equal to Q naught omega sin within the bracket omega t minus pi by 2. So now what is the voltage across the capacitor? The voltage across the capacitor is given by dc is equal to Q by 2. So that will be equal to Q naught by C cos omega t. Okay. Nothing but this equation. Q equal to Q naught cos omega t. Instead of capital letter Q, I am using small letter q. Okay. So in the circuit which I have drawn here, you can see the voltage across inductor and capacitor will be same, will be having the same value, and the sum of the energy, electrical and magnetic field energy in the circuit remains constant. So that will be given by Q squared by 2C, the electrical energy, plus half L I squared. That will be equal to the maximum energy, that is Q naught squared by 2C. So when the whole of electrical energy is converted to magnetic energy, your current is maximum, and in that scenario, your I naught, okay, that is, we know very well, L I naught squared by 2 will be equal to Q naught squared by 2C. So in this case, your I naught will be equal to Q naught by root of LC. So this is the mathematical treatment of LC oscillation. I hope you all can understand this concept. Okay. Do you all understand this concept, students? LC oscillation? Do you have any doubt?
No, sir.
One second, please. Okay, students, we shall resume now. So we will be discussing one numerical problem. We have only 5 minutes left. Okay, we shall be discussing one numerical problem. So a condenser of capacity capacity 6 microfarad is fully charged using a 6-volt battery. The battery is removed and the resistance left. And here resistance left 0.2 millihenry inductor is connected across the condenser. Across the condenser. Full stop. The current which is flowing through the inductor which is flowing through the inductor when 1/3 of the total energy, when 1/3 of the total energy is in the form of magnetic field in the inductor. Magnetic field in the inductor is option A 0.1 ampere, option B 0.2 ampere, option C 0.4 ampere, option D it is 0.6 ampere. Okay. It is 0.6. So you see a conductor of capacity 6 microfarad is fully charged using a 6 volt battery. The battery is removed and the resistance of 0.2 millihenry inductor is connected across the condenser. The current which is flowing through the inductor when 1/3 of the total energy is in the form of magnetic field is. Okay. So we have to find out the current. So total energy is initially in the form of electrical energy. So total energy initially U suffix E, that is half Q0 square, or you can also use this formula of CV square, because in the given data we have C and B. So C is 6 microfarad, 6 into 10 power minus 6 into voltage is 6. So the total energy is half CV square. So the magnetic energy is given by half L I square. In the question it is given that the magnetic energy is 1/3 of the total energy, 1/3 of UE. So that implies UB equal to half 1/3 of half into 6 into 6, that will be 3 into 6, 18. 18 into 10 power minus 6. So 18 into 10 power minus 6. This is equal to UB is nothing but half into Li square. L is nothing but 0.2 millihenry, that is 10 power minus 3 into I square. This is how you need to solve this problem. Okay. After solving this, you will be getting 0.6 ampere. This is how you need to solve this problem. Do you understand the concept, students? The
Yes,
question
sir.
and the solution. Do you understand?
Yes, sir.
Yes. Anyone have any doubt? Yes.
No, sir.
No, sir.
Anyone have any doubt, students?
No, sir.
No, sir.
So let us stop with this thing, and in our next class we shall discuss the concept of electromagnetic wave. Thank you so much for joining the session.
Thank you, sir.
Thank you, sir.
Thank you.